Hi everyone, welcome to week number 2 fluid mechanics for chemical engineering. This part is about the part number 3, and in part number 1 and part number 2 we have explored the mass conservation and energy conservation. In particular, in the second part we are constructing some important equation about the energy conservation, simultaneously considering mass conservation, which is called generalized Bernoulli equation. Please note that this generalized Bernoulli equation is, although a simplified version, it's not exact the governing equation we would like learn throughout this semester. But for a while, this Bernoulli equation is convenient to calculate the overall, the energy, the situation, and the balances. So in the week number 2 and part number 3, I'd like to finalize that how we can use this Bernoulli equation to calculate some important applications of the fluid mechanics in the chemical engineering. So in this part, we would like to focus on some specific apparatus, which is called orifice. Orifice is something like this. Inside of the cylindrical pipeline, as shown on your left-hand side here, we can put some barriers which have some tiny hole inside of this plate. It looks like a donut, some kind of depressurized donut. So we have some circular hole at the center of this plate. And this orifice is intentionally placed this tiny hole to control the velocity and just make the pressure differences before and after this orifice hole. And actually there is some sensor before and after of the orifice to measure the pressure differences. And this pressure difference will be used to calculate the flow rate. Or if you know the flow rate, maybe you can measure pressure difference too. Either way, this orifice is useful to measure the quantity of concerning the fluid. So it looks like something like this. So we have orifice here. As I said, this is some kind of this donut-like shape here. And this can be inserted inside of these cylindrical pipes. And we have a pressure sensor here. So there can be a variety of these shapes of the orifice, but they share similar principles for the working. So we have some unidirectional fluid on your left-hand side to the right-hand side, and we put this orifice here, and we define the radius of this orifice hole, and by calculating these energy balances around the orifice, and you can measure the pressure differences, and you can calculate the quantity of the fluid. So this is the movie, simplified movie, how this orifice works. So at the inset, you can find out that there is the relatively larger cross-section area here. But in the vicinity of the orifice hole, so we have the contracted areas, cross-sectional areas. And due to this contraction, and the mass conservation, the flow rate and the flow velocity is much greater than the initial flow velocity or our fluid velocity. But this means that we are increasing the kinetic energy, but due to the energy conservation law, it means that there is no horizontal position changes. Okay, so it means that there is no potential energy changes, but if we have increased kinetic energy, it means that we have decreased pressurization energies. That's why we have a relatively lower pressure, and that's why we have a pressure gradient at the orifice and inside of this inlet. And this is the working principle for the fluid mechanics, the measurement based on the orifice. Okay, so how we can apply this Bernoulli equation in this orifice situation? For that, the first job should be flow rate measurement. Actually, the flow rate measurement is done by discharge of the flowing stream into the receptacle. And there is some kind of the devices based on these Bernoulli principles such as orifice. And the flow of the liquid over the weir or notch is very important because we can guide the fluid. And actually by combining these principles, we can construct the turbine, a flow meter, or thermal flow meter, or some target meter, Coriolis flow meter, vortexing shear, and shedding meter. On your right hand side, you can find out some representative examples, which is composed of the reservoir. And if you put some holes, a series of the holes, as a function of the height, you can find out that there's some the falling curves here. And very interestingly, these falling curves have the same enveloped lines. So you can find out that it can derive these enveloped lines have some specific profiles, and I will let you know to talk about to work about this enveloped function profile the calculations. Okay, now we would like to apply the Bernoulli equation around the orifice systems. So first job is about the calculation of the kinetic energy and the pressurization energy, because you will have the same the height. So it means that you don't need to worry about the variations of the potential energy. And we will basically assuming that the mass conservation, and we have some contraction part for the original horse. So now we will take into account of this coefficient of the contraction coefficient. Okay, so according to the Bernoulli equation, this kinetic energy and the pressurization energy should be conserved. And this, due to this mass conservation law, instead of U2, you can take U1, A1 divided by A2. So here, so by calculating this left-hand side and the right-hand side, again, with respect to U1, you can calculate your U1 is equal to square root of the 2 multiplied by pressure differences divided by the density and this area factors -1. And please note that this P1 negative P2 means this U1 is non-zero, as it means that the P1 and the P2 is non-zero, and this pressure drop is measured using the manometer, as we have visited a few slides ago. So okay, so we have derived this U1 as a function of pressure drop and this contraction geometry. Now let me write again about this flow rate by multiplying this U1 multiplied by cross-sectional area A1. So instead of U1, we put this information here, and actually there's some more practical considerations such as discharge coefficient. Discharge coefficient is about the friction right after this plunging hole here. Anyway, this is the final form of this flow rate of the contraction factors, cross-sectional areas, and the discharge coefficient. So discharge coefficient is actually ideally 1, but in a reality, this discharge coefficient is always smaller than 1. And very interestingly, discharge coefficient itself is not a constant but a function of Reynolds number. Actually, we have not yet visited Reynolds number yet, a few weeks later, but let me first introduce that what is the physical meaning of Reynolds number. So Reynolds number is one of the representative dimensionless number frequently met in the fluid mechanics and in the chemical engineering. And this dimensionless parameter will measure the relative intensity of this kinetic energy relative to the viscous energy. So if you have the higher Reynolds number, it means that your fluid is moving very fast, or your fluid have very weak viscous friction. So Reynolds number is equal to density and velocity and some physical size divided by viscosity. And as you can see in this plot, which is actually discharge coefficient as a function of Reynolds number, so they have different types of value in the profiles due to the orifice profiles or orifice geometry. So it is important as a chemical engineer to set this discharge coefficient as a function of your Reynolds number and your orifice or some manometer geometry. So if you do not have exact information about your manometer or some your Reynolds number, you can reasonably infer from the references or some the past data set. So it is also important for the chemical engineer to track down these references and past data set, because it is not always available for the data to set this discharge coefficient and the other related important parameters. Okay, here are some several different types of this orifice related the pressure meter. So on your left top side, you can find the venturi flow meter. So it is some kind of the trapezoidal or some the reciprocal trapezoidal types. So we have some oblique like some channel which have some continuous contraction. Or we can have also Wk02 flow meter. So Wk02 flow meter means that we have some kind of this cone-like the plunges here, and they are just located at the center of this flow line. So it says that instead of the holes, they just block at the center, but we have some channels around these cones. So instead of holes, we have this kind of the annular holes around this cone here. But we can also apply the similar the principles measuring these pressure differences. And there's some orifice flow meter, and which is normal to say that we have some contraction given by these small areas, and you can measure P1 and P2, and by measuring these pressure differences, you can measure this quantity or some volumetric flow rate of this fluid. And lastly, we have some more more simplified version of this orifice. In this case, it is called the wedge flow meter. We have just a wedge here. Okay, so there is some blockade of the upper flow, and they are just enforced into the lower part. So that's why we have the higher velocity. But we will also have some kind of the divergence right after this wedge. So it has the same principle, operational principle, just as orifice. Okay, so I'd like to take an example for the Wk02 cases as shown on your right-hand side here. So we have pressure input and output, and right after this Wk02, we would like to measure these pressure differences. And it means that we need to measure the pressure drop, and we are given some quantities such as actual volumetric flow rate, constant for the calibration, inner diameter of the pipes, flow meter diameter, unit conversion constant, and the flow coefficient of the meter, density of the fluid, constant for the cone shape. Please note that this cone shape is not the simple cone, but we have some polygon types of cone. So for each of the cone shape, we have some specific value to consider the realistic situation. And finally, right after this cone, we need to also consider the fast expansion factors. So by combining these factors, we can construct some important quantities such as actual volumetric flow rate is a function of the constant of the calibration and the expansion factor multiplied by square root of the pressure drop divided by density. And actually this constant for the calibration is a function of this inner diameter and the constant of the cone shape and flow coefficient divided by some coefficient 2. And you don't need to worry about this coefficient because most of these makers will spontaneously give the important calibration constant, which is beta or some the CF, something like that. And by collecting the coefficient, all you have to do is just put this coefficient in front of this flow rate relation. So this is the relationship between this discharge coefficient, correction factor, and the Reynolds number. We have visited the similar plots, but in this plot, you can find out that we have some different dependence of this discharge coefficient as a function of Reynolds number, whether you select the battery flow meter, Wk02 flow meter, orifice flow meter, or wedge flow meter. So it is recommended for the engineers and the students to carefully select your flow meter, and once you got the information about your specific type of flow meter, you need to follow and track down the reference, the data set, and with this data set, you can use the interpolation or extrapolation, even if your Reynolds number is not shown in this plot. But I believe that most of the data points in your practice will be included in this reference plot. Okay, now let's take a look at some examples about some situations where this L-shaped pressure flow meter. So this is actually called pilot tube here. This is very narrowed down, and we are witnessing some spontaneous increase of the liquid inside of this pitot tube, and this pitot tube can be approximated as a type of this system, where the point number 1 and the point number 2. And by measuring this point number 1 at the position here is actually G1 is 0, and we measure this relative height changes, which is h plus d, and this at the point there is no movement of the fluid, so U2 is 0. And by applying these generalized Bernoulli equations from from point number 1 to point number 2, we can construct this energy conservation law. And please also remember from your first week such that the Pascal's law can be applied to the any type of this continuous fluid. So your P1 is actually P2 plus this water, the mass derived pressure, which is actually rho GD. Okay, so we have pressure differences, we have height differences. So now you can calculate by measuring this height in the P2 tube. And now you can finally calculate the U1 as a function of G and H. Okay, so this is, I think, the most simplified version of the meter. Now, finally, I'd like to invite you to look at more complicated the situations. And as shown in this figure, we are considering some mixed situation, which is actually we need to move some water from the river to the tank. And actually this inlet of the tank from the river is initially lower than the height of the water, but after some time, the water will rise above this height of the inlet. So it means that after this, there should be some changes about this situation. Okay, now so therefore we need to take the previous part and the later part by considering whether the height of the water is greater than this d or not. Okay, so let me first take the first part, which is the water height is smaller than the d. So in this case, we are witnessing the point number 1 and the point number 2. And in this case, G1 is actually H, G2 is D. Okay? And U1, there's no movement of water, so U1 is 0. And that's why we can apply the generalized verification. And when you take into account of this situation, the only remaining energy term is just potential energy. But at the point number 2, we have potential energy and kinetic energy. Anyway, U2, which is actually outlet at the floor, the velocity is actually square root of 2g and height differences. And if you set the V1 as the volume of the tank when the height is lower than d, and you can set the Q1 as our volumetric flow rate when the height is lower than d. Now you can calculate the time to fill this first half right before the height is equal to the inlet height, which is actually equal to AD divided by A, square root of 2Z, and H negative D. Okay, this is simplified. But what if your water height greater than this inlet height? So the situation is quite different from the previous part, because in these cases, we have P1, which is actually exposed to the atmosphere, so we have absolute atmospheric pressures here. But in these cases, the 2 point is actually not exposed to the atmosphere, but they are surrounded by water. So you need to recalculate the pressure P2, and which is actually equal to the additional water amount with the Pascal's law divided the driven atmospheric pressure. That's why we have additionally increased pressure here. And G1 is H, and G2 is 2, because 2 is fixed one. And U1 is still 0, and that's why we can calculate U2 as some kind of the square root 2g and h negative small h. And likewise, in these cases, you can calculate the V2 and the Q2 to fill this later part. And this is actually quite complicated relative to the previous part, but all you have to do is just integrate on your left-hand side and right-hand side, and you can finally calculate the time to fill the second part, which is equal to large A divided by small a multiplied by square root of 2h negative d divided by g. So in this example, please note that we have two different types of situations. The first one is actually your pressure is atmospheric pressure, and the second part is your pressure is atmospheric pressure plus water mass pressure. So by combining this situation, you can calculate the total time to fill the entire tanks from the river banks, and you can put the information from the problems, and you can find out that the total time should be about more than 2 hours.